Alright, so this is our Honors Chemistry section 11.3 lesson video part 3. So in part 1 we learned how to write complete ionic equations, and in part 2 we learned how to write net ionic equations. And so now we're going to focus on how do you know if something is going to be a solid or aqueous when it is a product in a reaction. And so that's called predicting precipitates. Is a solid precipitate going to form or is it not? So you can predict whether a precipitate forms by using solubility rules. If a substance is soluble, then it will dissolve in water and be aqueous. Okay, so when things are soluble, that means it will be listed as aqueous in the reaction. If a substance is insoluble, then that means it's going to bond with another ion and it will be a solid. So insoluble means you will have a precipitate and it will be a solid in the reaction. Alright, so you have a list of the solubility rules in your packet. However, if you've lost it or you're not even in my class, you can easily find some online. I will tell you though, depending on where you get it, they do vary slightly. Some of them, they have more exceptions and things like that. Some of them, they go into moderately soluble, but these are the ones that we'll be using. Okay, so you can see that all of these top ones, they're all soluble. So that means if I see NH4, I know it's going to be aqueous. If I see NO3, it's going to be aqueous, like that. Now, there's a couple, though, with some exceptions. So what this means is compounds that contain SO4 are normally soluble, except if they're with PB, AG, HG, BA, SR, or CA. Okay, so they're normally soluble. So if it's like Li2SO4, that will be soluble. But if it's PbSO4, it's insoluble. Okay, so these exceptions make it insoluble. All right, and one way to kind of remember that is BA, SR, and CA, they're all right in the same group on the periodic table. And then the AG, PB, HG happens to be the exceptions for both SO4 and Cl negative. So again, chloride is normally soluble, so for example, NaCl will dissolve and be aqueous. However, AgCl is insoluble since it's an exception. And then the bottom one just shows some insoluble ions. So we have carbonate, phosphate, chromate, sulfide, and hydroxide. All right, so those are some insoluble ones. So let's look at these and determine what's going on here. So the important thing to remember is if any part of the compound is soluble, then the whole thing is soluble. Because the thing is, insoluble wants to bond, soluble doesn't. So if one of them doesn't want to bond, it's not going to happen. Okay, it's going to separate and be aqueous. All right, so our first one says NH4Cl. Well, I can look back at my solubility rules and see immediately that NH4 is soluble, so it would be aqueous. All right, so this is what I'll be referring to when we do our next examples. So like I said, if you don't have this list with you, then you're going to have to kind of keep going back to this part. I'm not going to keep going back there. So I can see NH4 is soluble. All right, next well, I guess I'll just go back a couple more times just to show you. All right, so we have BaSO4. So when I go back to my solubility rules, I can see SO4 compounds are normally soluble, but Ba is an exception. So it would actually be insoluble, and so it would be a solid. So see, that one will be insoluble and would be a solid. All right, our next one, Na2SO4. Okay, I'm just going to click back this last time. I'm not going to keep going back. All right, so we have NaSO4. Okay, so SO4 is normally soluble. Na is not an exception. But the thing that people always forget is the group 1 alkali metals are soluble. So like lithium, sodium, potassium, those are all soluble. Okay, so the fact that it starts with Na shows me that it's soluble before I even look at SO4. Okay, so we're not going to click back anymore though. All right, so our next one, OH. If you look at the very bottom of your solubility rules chart, it is insoluble. So it will be a solid. Now our next one's where it gets a little tricky. K is a group 1 alkali metal. So it is soluble. But if you look at the bottom of your solubility rules chart, it tells you that phosphate is insoluble. So this is where this rule comes into play. If any part is soluble, the whole thing is soluble. So the fact that K is soluble means this would be soluble or aqueous. Okay, so this will break apart. It will not stay together. All right, so our next one, we have MgNO3. So one thing I didn't address yet is what happens when you have an ion like Mg that's not even on the solubility rules. If that happens, you just look at the other ion, okay, because not every element is on the solubility rules chart. Okay, so Mg is not on there, so I just switch over and look at NO3. So nitrate, if you look on your solubility rules chart, is soluble. So it will be soluble or it will be aqueous. And so all of these that are aqueous would not be a solid. So like you would not have a precipitate. Any of these that say solid or insoluble, you would have a precipitate if those ions had a chance to bond. All right, so our next one is AgCl. So if you look at your solubility rules chart, it'll tell you that Cl, chloride, is normally soluble, but Ag is an exception. So in this case, it's actually going to be insoluble and a solid because silver is one of the exceptions. All right, and then our last one, nickel is not on our solubility rules chart, so we just skip over it. Chromate is, it's at the bottom, and it's one of our many ions that is insoluble, so this would be a solid. Okay, so once you figure out whether something is soluble or insoluble, when you're writing a reaction, which I'll show you in just a minute, then you know whether to designate it as a solid or aqueous. All right, so let's actually put this to use now. So how can you predict whether a precipitate forms? So the rules for predicting precipitates are first you need to make your products, like figure out what the products are. Don't forget to balance your charges. Then you'll want to balance the whole equation. If you hadn't noticed, whenever we write a reaction, next thing we do is balance it. And then last, you need to identify whether the products are solid, liquid, gas, or aqueous. Okay, so I just showed you how to tell whether it's solid or aqueous using solubility rules. In the previous video, I showed you how to make the H2S gas, the CO2 gas, and liquid water using the sulfide and the carbonate ions. All right, so now we're going to focus mainly on the solid and aqueous, though, because we're going to use those solubility rules. So it says, predict the products for the following reaction. All right, well, I can tell by looking at this, it's double displacement because everybody's paired up. So what I'm going to do is I'm going to swap my two positives. All right, I'm going to go ahead and write my charges so I can just bring them over. So H is positive 1, Cl is negative, Ag is a transition metal, but since NO3 is negative, I know Ag is positive. All right, so now H is going to be with NO3. So I have H plus NO3 minus, so I don't need to cross anything. And now Ag is going to be with Cl. Remember, I'm going to write Ag first because it's the positive one. So Ag positive, Cl negative, so I don't need any additional subscripts there. All right, my next step is I need to balance the whole reaction. So I have Cl, Cl, Ag, Ag, NO3, NO3, H, H. So everything's balanced. So far so good. All right, so this part is nothing new. We've done double displacement and balancing already. This right here is the new part. Now I need to determine what state of matter my products are so I can figure out if there was a precipitate or not. If one of them becomes a solid, there was a precipitate. If they both remain aqueous, there was no precipitate. All right, so I look at my solubility rules. H is not on there, but it says NO3 is soluble. Soluble means it will be aqueous. So HNO3 is not going to be a precipitate. All right, next, I look at my solubility rules chart. It says Cl is normally soluble, but Ag is an exception. So that makes it insoluble, so this would be a solid. So in other words, this right here would be my precipitate. So if I mix HCl and AgNO3 together in a beaker, I'm going to see a solid form as a precipitate. Okay, now you have two options really. One of them can be a precipitate, one of them can be a solid, or they can both be aqueous, which means no reaction happens. You're not going to form two solids. Okay, so if you feel like they're both solids, you need to go back and look at your solubility rules chart again because you probably missed something. But remember, you don't have to have a precipitate form. Like some people, once they see they're both aqueous, they feel the need to force one to be a solid. I can mix tons of chemicals together and not have a precipitate. All right, so maybe if you're ready, try this one. Otherwise, you can watch me do this one. So it says, predict the products for the following reaction. So again, I can tell it's double displacement because everybody's paired up. So I'm going to swap my two positives. So I'm going to go ahead and put my charges. So acetate is -1, but since there's two of them, that's -2. So lead has to be +2 this time. Li is positive and Cl is negative. So I'm now going to put lead with the chloride. So don't forget to bring your charges over so that you'll remember to balance your charges. So I need 2 chlorides. All right, and then now lithium is going to bond with acetate, but of course I'm going to write lithium first since it's the positive. And then remember, acetate only has this 2 because it needs that 2 to balance with lead. It's not with lead anymore. So I'm just going to bring over acetate, not the extra 2. All right, so we have Li positive, C2H3O2 negative, so I don't need any additional subscripts there. So my next step is, of course, to balance the reaction. So I have 1 Pb, 1 Pb, I have 2 acetates, okay, 2 acetates. Here I just have 1 acetate. Remember, this 2 doesn't imply there's 2 of them. That's just part of acetate. Acetate is C2H3O2. So I put a 2 here. I have 1 lithium. Here I have 2 lithiums. So I put a 2. I have 2 chlorides and 2 chlorides. All right, so now I am ready to do the last step, and that is to determine did a precipitate form or not. Okay, so I'm going to put my little parentheses so I can figure out what's going on here. All right, so when you look at your solubility rules, you're going to see that Cl is usually soluble. However, Pb is an exception, making it insoluble, so it will be a solid. So see, this right here will be a precipitate. Whoop. All right, over here, lithium is a group 1 alkali metal. Group 1 alkali metals are soluble, so this will be aqueous. So if I mix these 2 solutions together, I am going to form a precipitate, and my precipitate will be lead 2 chloride. All right, and so that is how our solubility rules work. All right, so let's move on. Okay, so if you didn't try the previous one, try this one on your own. Okay, it doesn't help if you just keep watching me do it. So pause it, I'll assume you've done it, and let's look at it together. All right, so again, I can tell it is a double displacement because everybody's paired up. So I'm going to swap my 2 positives. So first, let me go ahead and put my charges. So ammonium has a +1, chloride's -1, barium's +2, nitrate's -1. All right, so now ammonium is going to bond with nitrate. So I have my ammonium, and then nitrate, the important thing is this 2 is only here because it was bonded with barium. It's not bonded with barium anymore, so I'm just going to bring over the NO3. And see, when it's with ammonium, it doesn't need a 2 because their charges already cancel out. All right, next, barium is going to bond with chloride. But I'm going to write barium first because it's the positive one. And I do need 2 chlorides in this case in order to balance those charges. All right, so I've made my products. Now I need to balance the whole reaction. So I have 1 ammonium, 1 Cl, but here I have 2 Cls, so I need a 2. But before I continue, now I have 2 ammonium, so I need to go back and put a 2 here. I have 1 Ba, 2 nitrates, 2 nitrates. So everybody's balanced. So last step is let me determine, am I going to get a precipitate or not? So if you look at your solubility rules, you can look at either one. Ammonium and nitrate are aqueous. Are soluble. And so soluble is aqueous, so this will not be a precipitate. And then Cl is normally soluble, but it has some exceptions. However, BA is not one of the exceptions for CL. It is an exception for SO4, but it's not an exception for CL, so CL will be soluble, and this will also be aqueous. So in other words, in this reaction, there is no precipitate. There's no precipitate in this reaction. All right, and that's okay. Like I said, don't feel like you gotta force it to have. Lots of times when we mix things, we don't get a precipitate. So hopefully you got that one right. All right, so again, maybe try this one that we'll look at together. This one's a little trickier because I don't even give you the reactants, I give you the names. So hopefully you're getting good at writing formulas. So this one also has a little extra step. It says write the net ionic equation. So we're gonna write the equation first, then do the net. So maybe don't try this one on your own. I think there's one like this next. So maybe you just watch me do this one. So it says write the net ionic equation for the precipitation reaction. So in other words, they're telling me there is going to be a precipitate. For the precipitation reaction that occurs when solutions of calcium chloride and sodium carbonate are mixed. So see how they told me they're solutions? So without even using my solubility rules, I already know that means they're aqueous. However, let's just pretend like you didn't know. I'll show you how to tell. All right, so we have calcium chloride. So calcium is Ca with a positive 2. Chloride is Cl negative 1. So I'll cross my 2. And sodium carbonate. So sodium is Na positive 1. Carbonate is CO3 negative 2. So I would need 2 sodiums. And it says they are mixed. All right, so again, because they told me it was solutions of those, I can assume they're aqueous. However, like I said, say you didn't know that. Well, you can see that chloride is normally soluble with some exceptions. However, Ca is not an exception, so this will be aqueous. And then Na is a group 1 alkali metal, which is soluble. So it doesn't matter if carbonates tend to be insoluble. Sodium is soluble, so it is also aqueous. All right, so I can see it's going to be double displacement because I see there's 2 things that are paired together. So I'm going to swap my 2 positives. All right, so now Ca is going to be with CO3. So I'll write the Ca first because it's the positive one, CO3 next. And I don't need to cross anything, they already cancel. Now Na is going to be with Cl. But for both of these, the only reason the 2's are here is to help balance what they were bonded to. They're not bonded to those things anymore. So I'm just going to bring over 1 Na positive. I'm putting Na first because it's the positive one. 1 Cl negative. Alright, so next step is I need to balance my reaction. So I have 1 Ca, 1 Ca, 2 Cls, 1 Cl. So I'll put 2. 2 Nas, 2 Nas, and a CO3 and a CO3. Alright, so last step is because I need to write the net ionic equation. I got to figure out what state of matter these are in. So if you look at your solubility rules chart, it tells you CO3 is normally insoluble, making this a solid. It will tell you that Na, which is a group 1 alkali metal, is soluble, making this aqueous. So see, now that I know everything I need about the reaction, I can go through and get rid of my spectators. Alright, because remember, I've got to get to the net ionic for this one. So I can see calcium was aqueous, now it's solid, so it did something. Chlorine was aqueous, it's still aqueous. So the chloride ion did nothing. So I can get rid of that. Sodium was aqueous, and it's still aqueous. So sodium did nothing. And then carbonate was aqueous, and now it's formed a solid. And so then I just pull down what I'm left over with. So calcium, positive 2. Remember, when you're writing it as an ion that's aqueous, you have to put the charge. And then carbonate, CO3 negative 2. And then it forms our solid. And so remember, once it bonds, you don't need the charges anymore. However, if you still put them, I'm not going to mark that wrong. All right, so that's all you have to do. So it's just kind of combining net ionic equations with predicting precipitates. And so again, there's a lot going on. There's lots of room for error. So just work slowly. Make sure you're balancing charges as you go. Make sure you're picking the right charges. Okay, so this one's just like the one I just showed you. So maybe pause the video, try this one, and then them together. So again, write the net ionic equation for the precipitation reaction that occurs when aqueous solutions. So y'all, this one, it gave me even more of a hint. It sat there and told me they're aqueous. Aqueous solutions of silver 1 nitrate and potassium phosphate are mixed. All right, so let's start. So I have silver 1 nitrate. Well, silver is Ag. The 1 means it has a positive 1 charge. Nitrate is NO3, and it has a negative 1 charge. So my charge is already balanced. I'm going to just go ahead and say it's aqueous because this time it literally told me in the question. And it's mixed with potassium phosphate. So potassium is K, which has a positive 1 charge. Phosphate is PO4, which has a negative 3 charge. So in order to balance, I need 3 potassiums. And it is also aqueous because, again, they told me the solutions are aqueous. However, if they hadn't, I could have just looked at my solubility rules. Nitrate's aqueous, group 1 alkali metals are aqueous. So both of them are soluble, so both of them will be aqueous. All right, so again, I can see this is a double displacement because I have 2 things that are paired. So I'm going to swap my 2 positives. So now Ag is going to be with PO4. So I have Ag positive, PO4 negative 3. And of course I put Ag first because positive is always listed first. So I need 3 silvers to cancel out my negative 3 charge. And now K is going to bond with NO3. However, K only has this 3 because it was bonded with phosphate. It's not bonded with phosphate anymore. So I'm just going to bring over 1 K and an NO3. So see, when it bonds with NO3, it doesn't need a subscript. I'll fix the fact that there were 3 on that side and there weren't this side when I balance. All right, so that brings us to our next step. We need to balance. So I have 1 Ag, but here I have 3 Ags, so I'll put a 3. I have 3 nitrates. Remember, nitrate is NO3, so there's not 9 of them. I have 3 nitrates, and here I have 1 nitrate, so I need a 3. I have 3 Ks, a PO4, and a PO4. All right, so everybody's balanced. So next step is I have to figure out, okay, well, are these solid or aqueous? So I go to my solubility rules. Well, PO4 is at the bottom of your solubility rules. It says it's insoluble, making it a solid. K or NO3, both of them are on there, are both soluble. So this would be aqueous. So I still need to get to my net ionic equation. I know, again, these seem like they take forever, but when you get good at them, like, you actually can do these pretty fast on your own. It takes me forever because I have to explain every step I'm doing. All right, so silver was aqueous. It is now a solid, so it is not a spectator ion. NO3 was aqueous. NO3 is still aqueous, so I can get rid of NO3. K was aqueous. K is still aqueous, so I can get rid of potassium. PO4 was aqueous. It has now bonded and formed a solid, so I need to keep PO4. And so then I just pull down what I have. So I have 3 Ag positive, aqueous. I have PO4 negative 3, aqueous. And that forms Ag3PO4 solid. And so remember, when you're writing the ions by themselves in the aqueous form, they have to have their charges, but once you bond them together, the charges aren't necessary anymore. All right, so hopefully you got that right, or if you didn't get it right, hopefully you were at least on your way to getting it right. This is a long problem, and there's lots of room for tiny mistakes, so even if you only got part of it right, you're doing good. All right, so let's knock out this section assessment. So what is a net ionic equation? A net ionic equation has no spectator ions, and it only includes the substances that actually react in a reaction. Okay, so a net ionic equation has no spectator ions, and it only includes the substances that react in the reaction. So number 2, how can you predict the formation of a precipitate in a double displacement reaction? Well, you just use your solubility rules. If something is insoluble, you formed a precipitate. Okay, so for number 2, you just use your solubility rules. So number 3, it says write the net ionic equation for the following reactions. Okay, so I'll show you the first one and then maybe you try the second one. All right, so first step is I need to balance. So I have 1 PB, 2 acetates, and 1 acetate. Remember, this whole thing is just 1. So I need a 2. I have one Cl, two Cls, so I need two hydrogens and two hydrogens. All right, so let me go through and knock out my spectators. So Pb was aqueous, it is now solid. Acetate was aqueous, it is still aqueous, so I can get rid of acetate. H was aqueous, it is still aqueous, so I can get rid of it. So see, it's like steps like these that you wouldn't sit there and do this on your own. You're not going to sit there in your mind and be like, oh, okay, which one's aqueous on both sides? Like, you'll do all this real fast in your mind. All right, Cl was aqueous, and now it's solid, so I need to keep that. All right, so remember, when it's an ion, I have to have the charge. Well, lead can have multiple charges, so I've got to figure out what the charge is based on what it's bonded to. So acetate has a -1 charge, but there's 2 of them, so that's like -2. So lead has to be +2. So I'm going to bring down lead with a +2 charge, and it is aqueous, plus, now this is where you got to be careful. We got rid of H, but there is still a coefficient that applies to Cl. So 2Cl, which has a negative charge, aqueous, yields our solid, PbCl2 solid, just like that. All right, so maybe pause it and you try this one, and then I'll assume you've done that. We'll look at it together. So my first step is, of course, I need to balance. So here I have 2 ammonium. Here I only have 1 ammonium. So I need a 2. Remember, it's not 4, it's just 1 of them. Here I have 1S, 1S, 1CO, 1CO, 2 nitrates, 2 nitrates. So I have everything balanced. So let me get rid of my spectators. So ammonium's aqueous here, it's still aqueous here. So I get rid of it. S is aqueous, but now it has become a solid. CO was aqueous, but now it became a solid. NO3 is aqueous, and it is still aqueous, so I can get rid of NO3. All right, so then I just bring down what I have left. So S has a -2 charge, and it's aqueous. Now CO can have multiple charges. So NO3 is -1, but since there's 2 of them, that's like -2, so CO is +2. I'm going to put my aqueous, and then that forms my solid, which I don't mess with the solid. Don't mess with the solid, liquid, or the gas. Just leave it alone. All right, so hopefully you got that one right. And by the way, I know if you're thinking like, golly, net ionic is way faster than complete. The good news is we use net ionic more often than complete anyway. So that's a positive at least. All right, so last 2. So maybe let me try the first one, then you try the second one. So it says predict the product. So this is where I need to figure out, am I getting a precipitate or not? All right, so I can see that this is going to be double displacement because everybody's paired up. So I'm going to swap my 2 positives. So let me go ahead and put my charges. Na is +1, PO4 is -3. Chromium can have multiple charges, but since Cl is negative and there's 3, that's like -3. So chromium is +3. So now sodium is going to bond with the chloride ion. However, both of these only have the 3s because of who they were bonded to. They're not bonded to those ions anymore. So I'm just going to bring over Na positive, Cl negative. Like, see, there's no reason to have 3s on this side. Like, they already cancel out. All right, and now chromium is going to bond with phosphate, but I'm going to put chromium first since it's the positive. And see, +3, -3 cancel, so I don't need any additional subscripts. So next, I need to balance the equation. So I have 3 sodium. Here I just have 1, so I'll put a 3. I have a PO4, PO4. I have a chromium. I have 3 chlorides and 3 chlorides. So I got it balanced. So last step is I need to determine, am I going to make a precipitate or not? So if you look at your solubility rules, Na is a group 1 alkali metal, and those are soluble. So this is aqueous. If you look at your solubility rules, PO4 is insoluble, which means this will be a solid. So this right here will be my precipitate. So if I mix these 2 chemicals, like a solution of each of these chemicals, I am going to get a precipitate. All right, so maybe pause the video, you try our last one, and then we'll look at it together. All right, so again, I know it's double displacement because everybody's paired up. So I'm going to swap my 2 positives. I'm going to go ahead and put my charges. Aluminum is +3, sulfate's -2, NH4 is positive, OH minus is, or OH is negative. So now aluminum is going to deal with hydroxide. However, aluminum only had the 2 because it was bonded to sulfate, so I'm going to get rid of the 2. So aluminum's positive 3, I'll put it first because it's the positive. Hydroxide's negative 1. And again, y'all, don't fall into this trap. We need 3 hydroxides. Even though it doesn't already have its own subscript, it's still a polyatomic ion. So I have to have the parentheses around it before I put the 3. Now, NH4 is going to bond with sulfate. But again, sulfate only has this 3 because it was bonded to aluminum. It's not bonded to aluminum anymore, so I'm just going to bring over SO4. All right, but I'm going to write the NH4 first because it's the positive one, and the SO4 second. But SO4 has a negative 2 charge, so I need 2 ammonium. Okay, so we're almost there. So next step, of course, or last step really, is to determine am I going to form a precipitate or not. So if you look at your solubility rules, it will tell you that hydroxide is insoluble, making it a solid. If you look at your solubility rules for either of these, it will tell you they are soluble, which makes it aqueous. So in this one, again, I will have a precipitate. But remember, it's okay if you don't have a precipitate. Not every time you mix 2 chemicals together are you going to get a precipitate. All right, so the main thing on this is be careful. Make sure you're crossing your charges. Make sure you're balancing the reaction. And then make sure you understand how the solubility rules work.